Hello everyone. Today we're going to be talking about pH and pOH. So hopefully we've all heard of pH at this point from middle school and from our discussion of acids and bases earlier. Today we're going to be talking about what that actually is, as well as pOH, which goes right along with it. So we've seen the pH scale before. We know it goes from approximately 0, which is very acidic, all the way up to 14, which is basic, also known as alkaline, with 7 being neutral. So the pH scale tells us how acidic or how basic a solution is. What it's actually measuring is the H plus concentration of the solution. And while we say H plus, because that's the easiest way to visualize what's going on with acids, the hydrogens aren't actually floating around by themselves. You'll often see them written as hydronium or H3O plus. For the rest of this unit, moving forward, H plus and H3O plus, these are going to be the same. If you see one, it means both. And it measures these concentrations using what we call a logarithmic scale. So you guys have probably seen log on your calculators before. Log stands for logarithm. And what a logarithmic scale is it means that for every one step you increase on that scale, like going from 1 to 2, 2 to 3, 7 to 8, you're not increasing by a value of 1, you're actually increasing by a magnitude of 10, or 10 times. So going from a pH of 3 to a pH of 2 is actually 10 times as acidic as it was before. We see logarithmic scales other places. The Richter scale for earthquakes, going from a 7 to a 6, that's also on a logarithmic scale. So a 7.0 earthquake is actually 10 times stronger than a 6.0 earthquake. The Mohs scale of hardness, if we've taken a geology sort of course before, how hard something is, I'm pretty sure it's also measured on a logarithmic scale. So that's the pH scale. We've seen that before. The pOH scale is very similar. However, instead of focusing on hydrogen ion or hydronium ion, it's focusing on hydroxide, just like the pOH here would imply. So the pOH scale tells us how basic a solution is. And it measures the hydroxide or the OH minus concentration using that same logarithmic scale. It also goes from 0 to 14. Can't see behind me. 0 to 14 here. And it's inverted compared to the pH in that if you have a very high pOH, like 14, that would mean that you're very acidic, versus having a very low pH means you are also very acidic, right? So if you have a low pOH, that means you're very basic. So they're sort of flipped. And then the easy way to convert between the two is that we know the sum of the pH and the pOH is always going to be equal to 14. So if you have a solution, let's say a pH of 2, you know that the pOH of that same solution is going to be 12, right? Because 2 plus 12 is equal to 14. Similarly, when it's right in the middle, if you have a pH of 7 and a pOH of 7, it's equal to 14. Same the further you get to the right. So take a second and think about if you had a solution with a pH of 3, what would the pOH be? Then also consider whether it would be an acidic or basic solution. So if we have a pH of 3, that would be over here on the left-hand side of our acid-base scale. The pOH, the sum of 3 and 11 is equal to 14. So the pOH would be 11. The pH of that solution would be 3. And it would be an acidic solution because we have a low pH and a very high pOH. So the pOH would be 11, the pH would be 3, and it would be an acidic solution. So going a little bit into what you'll learn later on in math, if you haven't been exposed to logarithms already, what are logarithms? How do they work? What's going on here to allow us to actually use a logarithmic scale? So we're going to start off with an example. Hopefully you have your calculators. You can also have your phone calculator. If you turn it horizontal, meaning lengthwise, you'll get an extended sort of calculator that will give you the log options here. So take a second and plug this into your calculator. Take the log of 100, the log of 1,000, and the log of 10,000, see what you get. So if you have a standard calculator, all you have to do is hit the log button. That'll pop up log with an open parentheses here, plug in the number, close the parentheses, hit enter, you're good to go. For an iPhone calculator, it's a little more complicated. What you have to do is, again, turn it horizontal, type in the number first, so you would type in 100 here. Then, right next to the 4 there, you'll see log base 10. It's the same thing as just normal log on a normal calculator. Hit that button after you've plugged in the actual number, you will get your answer. So, if you did it correctly, log of 100 is equal to 2, log of 1,000 is equal to 3, log of 10,000 is equal to 4, right? So you're factoring up or scaling up by a factor of 10 here, whereas your answers are just going up by an increment of 1. This is why logarithmic scales work the way they do, why going from a pH of 2 to a pH of 3 is increasing by a factor of 10. What taking a logarithm of a number does is essentially it does 10 to the x equals that number, and then it solves for what this exponent right here is, right? So if we have 10 to the x equals 100, 10 would have to be raised to the second power to get to this value of 100 here. So the answer of log of 100 would be 2. For 1,000, it would have to be 10 to the third power in order to be equal to 1,000, right? That's 10 times 10 times 10. So if we took log of 1,000, we get 3 as our answer. Same thing with 10,000, right? It scales, so 10 times 10 times 10 times 10, or 10 to the fourth power, ends up being equal to 10,000 here, which is why log of 10,000 is equal to 4. So how do we use this information to solve for pH, pOH, to figure out what the concentration of H plus and OH minus are? If you're going to write anything down from this lesson, it's probably the stuff on this slide here. So here's a list of the formulas we're going to be using. To find pH, again, we're focused on the hydrogen ion concentration. This could also be hydronium, H3O+, either work. What you're going to do is you're going to take the negative, that's important, you can't forget that, the negative log of the hydrogen ion concentration. That will give you the pH of that solution. So, for example, if I have a 0.001 molar hydrogen ion concentrated solution, if I take the negative log of that concentration, I would get 3, meaning my pH of that solution would be 3. For pOH, it's the exact same process, except instead of focusing on H+, you're focusing on hydroxide here. So to find pOH, you take the negative log of the hydroxide ion. So again, if I had a basic solution with 0.0001 concentration or molarity of hydroxide, if I take the negative log of that value, I would get 4. If you're practicing plugging these into your calculators, again, a couple things to keep in mind. One, it needs to be the negative sign, not the subtraction sign. If you do subtraction log of a number, you're going to have a bad time. It'll give you syntax error or something like that. Be sure to plug the negative sign in here. If you're using a phone calculator, again, you sort of have to work backwards. You're going to plug in the concentration, so 0.001, then hit the logarithm button, then change the sign using the negative here, and you'll end up with 3. So, to go backwards, if we have the pOH and we want to get the concentration of hydroxide from that, we have to take 10 and raise it to the power of the negative pOH. This is essentially the inverse operation of a logarithm. Just like to undo addition, we have to subtract. To undo multiplication, we have to divide. This is the same process. This is you undoing that logarithm that was taken in order to find your pOH. So say your pOH is 4, like from the previous example. If we do 10 raised to the negative fourth power, we're given our hydroxide ion concentration, which you'll note is the exact same as we have here, right? You're just undoing that operation that we did previously. Same idea for finding the H plus concentration when you have your pH, right? It's 10 to the negative pH will give you your hydrogen ion concentration here. So just like in our first example, if we have 10 to the negative third power, we end up getting 0.001 molarity as our concentration of hydroxide. Last tool we're going to be using is again the fact that the pH and the pOH when added together will always equal 14. So if we're given the pOH, we can find the pH just using simple subtraction. Okay, so now some examples that will be very similar to your homework. I want to know what is 1, the pH, 2, the pOH, and 3, the hydroxide ion concentration of a solution that has hydronium ion concentration of 0.025 molar. So I'm given my hydronium ion concentration here. Based on the previous slide, I can use the formulas from there to find the pH using this equation here, right? I know the pH is equal to the negative log of the H plus or H3O plus. Again, those are the same concentration. I have that, so I can just take this and plug it right into my equation here. So if I do that, I end up getting pH equals negative log of 0.0025. If I plug that in, just like I told you previously, depending on what calculator you're using, I end up getting a pH of 2.60. So as a rule of thumb, for sig figs, for pH, you take the number of sig figs you have, so in this case 2, and that's the amount of decimals that you have for your pH or pOH here, and vice versa, right? But for now, for our purposes, as long as we go to 2 decimal places, I'll say that's fine. So now we have our pH, right? We have our H3O plus concentration. From the pH, we can find the pOH because we know that the pH plus the pOH has to equal 14. Take a second, think about what the pOH would have to be so that when you add 2.6 to it, you get 14. So again, once you know the pH, you can find the pOH because you know that the sum is equal to 14. So 2.60 plus the pOH equals 14. If you subtract 2.60 from both sides, you end up with pOH on the left-hand side and 11.40 as your pOH of the solution. Similarly, now we have our pH, right? Check the first box. We have the pOH, we check the second box. We just need the hydroxide ion concentration. And given that we now know the pOH, we can solve that using this equation here, which again was on the previous slide. So once you know the pOH, which we just got as 11.4, we can find the hydroxide concentration because we know that the hydroxide ion concentration is equal to 10 to the power of negative pOH. So 10 to the power of negative 11.4. Take a second, plug that in, see if you get the right answer. So you're raising 10 to a very, very negative power here. So you're going to get a very small number. Again, think back to scientific notation, how we did that. Instead of writing 0.0 with 11 zeros, 398, you can put it in scientific notation here. If you're using the iPhone calculator, if you just turn it back up vertically, it'll put it in scientific notation for you. Just keep in mind that that E that you're seeing is the same as times 10 to the. So you get 3.98 E negative 12. That's giving you this exact number we see right here. Okay, so now we've answered all 3 questions that this question here posed, and we have all 4 units that would be potentially useful here. So let's do one more example. I want to know, same question essentially, right? The hydroxide ion concentration, the pOH, the pH, and the H+. So there's 4 different things that's being asked of us here of a 0.0001 molar calcium hydroxide solution. So this one requires a little more thought because here we're not given the hydroxide ion concentration. We are given the concentration of this salt here, of this base, calcium hydroxide. So if you think back to our first lesson from this unit, we talked about having monoprotic, diprotic, polyprotic acids, right? Not all acids release the same number of hydrogens as other acids. So for any acid or base that has one or more than one H+, or for bases, hydroxides, like we do here, right? Calcium hydroxide has 2 hydroxides, since our cation has a 2+ charge. The molarity of the compound, which in this case is 0.0001 molar, must be multiplied by the number of hydrogens or the number of hydroxides. So again, we're given the concentration of the salt, but what we care about is the concentration of hydroxide. And for every 1 calcium hydroxide here, it's breaking apart or dissociating into 1 calcium and 2 or twice as many hydroxide ions. So our concentration of our salt is actually going to produce 2 times that concentration, or 0.0002 molar hydroxide ion solution. So that's something important that we need to think about before we do any of the calculations from the previous example. But now that we have that, right, we can proceed just like we did before. So same problem, right, just on a new slide. We know, because we just solved it on the previous slide, that our hydroxide ion concentration is 0.002 molarity. So we have one of the 4 now. From that, right, we can find the pOH using this equation. Take a second, plug that in. Hopefully, we get something around 2.70 again. Rule of thumb, I'm going to use 2 decimal places for my pH and pOHs here. Now, I can find my pH. Again, this is our pOH here. I can find my pH because I know that this value of 2.7 plus whatever the pH is going to sum up or equal 14. So my pH plus 2.70 equals 14. If I subtract 2.7 from each side, I will have my pH, which in this case equals to 11.3. Okay, now I have my hydroxide ion, I have my pOH, I have my pH. Last thing I need is my hydrogen ion concentration. I can find that, again, using the equations from that slide with all the equations on it right here, right? I know that my H+ concentration is equal to 10 to the negative pH. And I know my pH is 11.30. We just solved for that. So by plugging this into the calculator, 10 to the negative 11.30, I should get my hydrogen ion concentration, which ends up being 10 or 5.01 times 10 to the negative 12 molar. There you have it. That's how we would find the hydroxide ion concentration, the pOH, the pH, and the H+. So given any one of these 4 things, using the tools and the equations given to you, you should be able to find all of these 3.